The title of my talk is Debugging AI. I made it deliberately ambitious because I'm chasing two rabbits here. I'm trying to address stakeholders, explaining what you should expect from your AI problems, try to debug their perception and their expectations. And on the other hand side, for the engineers here and for the developers, give you some hands-on tooling on what to do in your AI project. So AI is not really a new term. You all know that. But artificial intelligence was coined as a term in 1956. The term artificial neural network even dates further back to 1943. I'm not quite that old, but I'm in artificial intelligence since like 1995. Got my PhD in that area and deployed like diagnosing systems to large printing machines. I've deployed medical expert systems. I've worked in stuff with knowledge representation. That's the thing you saw from Laurent with that identifiers for people and objects and concepts. And I have worked in natural language processing. So I've seen some ups and downs in artificial intelligence. Luckily, I'm after that period, which was termed AI winter, when everybody was down and AI was like, that's never going to work. But I've seen some up and downs, and like for the last 10 years or so, we see a really an hype in AI. And that's very important to understand why we see that hype and what this means for your project. And one thing, I've never ever seen a technology mentioned alongside the term magic so often as in AI in the last 10 years. And AI is nothing like magic. It's mathematics, it's a set of mostly very simple engineering tricks, and it's nothing like magic. I have 6 factors right now to explain the current hype. Magic is not one of them. One of them is compute power. You all know that the usage of GPUs, or Laurent mentioned it, Google is deploying their own hardware for machine learning. That's more compute power than we had in the 90s or when neural networks came up. But it's not only the mere compute power, it's the ability to buy it by the minute. So you don't have to create large infrastructure you throw away after your training. That's very important. So what I show here is quite the opposite of that. It's a remote control car, self-driven by a Raspberry Pi, and you should definitely watch that video I linked. Very impressive on what's possible on that little machine. The other factor is more data, because it's twofold. More data, which is necessary for learning, is now available. It's no coincidence Google is in the front of machine learning, because in their effort to map the internet and to provide their search-based businesses, they gathered a lot of documents, they gathered a lot of pictures and of videos and whatever. And in order to improve what they're serving, they had to make sense of that. And machine learning, Laurent showed it to us very impressively this morning. Machine learning is right for that. But on the other hand side, that massive amount of more data makes it absolutely necessary to have some automated solution to cope with that amount of data. And so you can have a competitive advantage when applying AI over some handmade or whatever solution, which is not as good, and scaling it to the global market makes the cost like handleable. But we're not all Google. That's very obviously. But there's something more. I cited a report which is like, I think from about a month ago, from a venture capital company on what is AI and what's driving the hype of AI, and say that, and they're not the only ones, that speed of development is really important. I've read that and I thought about it and well, speed of development, like having AI doesn't make my developers, doesn't make you and me really faster or more driven or whatever. So I think you have to be very careful of the term speed of development. What it brings to you is the ability, once you've solved a problem, to solve the problem again faster if it changes. So if you have solved a problem like to find the Eiffel Tower, to stay in Laurent's examples, you can apply the same techniques to find another building, like the Empire State Building or whatever. All that leads to high valuation and lots of money, which is attracted by that. We see a huge amount of growth, and it's a self-fulfilling prophecy here to some extent. More money means more projects, means more compute power, more models, and hopefully more outcome, leading to again more money. I'm a little bit skeptical on how long this really goes on, but you have to know. And there's another factor I rarely see mentioned, but I think it explains a lot on what kind of projects you see. I've been at the Solutions Conference last year in Hamburg, and there were several AI projects, and some of them were like, why on God's earth do you act like this? Why is this a project? Why are you transferring your manual into an app which is powered by computer vision? It's like way too much stuff. And I think the last factor to know of is fear. Is a fear to lose speed of development, to lose the access to all those opportunities, to lose access to the global market. And it's important to understand those factors because these factors are impacting your AI project. As a stakeholder, you have to cope with that, or you have to drain that flow of money or whatever. And as a developer, that's basically the thing where your KPIs come from. Okay, enough of what's driving the hype. What is AI? We saw some examples today. First of all, we have to separate strong AI from weak AI. Strong AI is where you really try to create something that is intelligent in a sense like you and I. The most popular term for this is a Turing test. Strong AI would be able to pass the Turing test, so to fake being like having a sense of itself or whatever. And weak AI is where we all are. It's applying a set of tools to solve a specific narrow problem. Like computer vision is nothing like strong AI. If you can label what you see on a picture, you have no sense of the world around you. You just attach textual or identifiers to images. That's a narrow task. So for me, and I just apply that to you, AI is a set of tools to cope with a set of problems. And the rest of my talk will go into the properties of both the problems and the tools. Machine learning is just a subset of those tools. It's not one tool, it's many tools, and it's a subset. Others are, for example, knowledge representation, or planning how to get from A to B, or reasoning. And one thing to know, that most of the AI stuff is following not Boolean logic, what we usually know from programming, but probabilistic logic. We'll see later on why this is important. This is a typical AI problem. I can't see really anybody. Do you spot something weird here? Show of hands, who's finding what's not like it should be? Nobody? Or all of you? It's the order of the adjectives. In an English sentence, you have like rules for what kind of, or what ordering you should use. So, although there are rules, most of the people don't think about them. I would go even further. Most of the people speaking English, also native speakers, are not able to formalize those rules or the mechanisms of building a sentence with proper adjectives. Just implicit knowledge, something you learn and you build up experience with. And it's the first property of our AI, of problems which match AI. It's problems we have no formalized knowledge or no knowledge at all. And this makes it hard for traditional programming. Like with that example of the Eiffel Tower, it's really hard to code a rule-based or hard-coded tool to recognize whether an image contains the Eiffel Tower or not. Also, those problems are usually afflicted with uncertainty. Like, for example, if you try to diagnose a machine, sometimes the sensors are broken. And you can't read the values from those sensors. And your AI system should be able to cope with that. That's basically what I mean here. Sometimes you don't have the answer, so it's unknown, and you have to cope with that. And the thing I already mentioned is problems changing rapidly. Not completely different problems, but problems which change over time. I picked a very special example where I can make some of the points clearer, hopefully. A relatively old-fashioned thing in AI is to play games. First, it started with chess. Nowadays, like I don't remember when, 5 years ago or 4 years ago, AlphaGo was able to beat the world's best Go players. But the mechanisms behind these are always the same. The problem is when you look at a state of a chessboard or a Go board, there are no rules which move is or which turn is the next best one. So you have to find out by searching all the possible moves, which is a line from my state representation to the next state representation, and you have to look at like all possible moves. But looking at all possible moves would be really, really costly. In chess, this tree which unfolds has like a branching factor of about 30, and with Go it's like 250. I'm neither a professional chess player nor a professional Go player. I have no clue whether that's correct, but I guess it's about that amount. So branching out and watching the complete tree unfold is not an option. So to cope with that problem, you have to have an evaluation function which gives you an indication of what to do next or where to look next. and you simply take the best option and follow it down, like repeating it over and over again. With chess, like in the 90s or even 20 years ago, you had experts able to tell you whether a given configuration of a board is a good one, is a stable position, is one where you can defend your figures or and stuff. That's as far as I know, not really true for Go. It's much more complex. So in designing AlphaGo, Google had to make another move. They had to find out which function to use use as a heuristic. And you do that, or you can do that, by another machine learning, by another artificial intelligence technique. It's called reinforcement learning. It's, you know, the result of something at the end of a stream of events, and you propagate that result back onto the events in that stream that led to that result. And with that propagated values, Google trained a neural network to act like the evaluation function. That's why I chose this problem, because it sounds really simple, but in fact you need to aggregate like 4 different AI techniques, and that mechanism basically boils down to supporting every heuristics-based search. And I think, that's my guess, Google did that not only for the researching part and for the war of talent they can fire on with that, but a very, very popular heuristic search application is navigation. Google Maps, I think, can profit a lot from that. It's guesswork, but that's one possible explanation why they went into that. Okay, I'm digging deeper. You remember the properties of the problems, and I want to go into how to debug actual AI software. One thing you need to know and need to understand is the properties of the problem make debugging really hard by design. As a problem has special complexity, so does the solution, and so does the verification of that solution. And with that internalized or unknown knowledge I talked, this is classically the most depictive story of that is of medical diagnostic problems, where you need to find out which is the right diagnosis and which is the right therapy for a set of symptoms. And given any patient, you just don't know. A physician is just trying to exclude unlikely solutions to that. And sometimes you won't even know. Okay, we're here on e-commerce talk. You say, how is this related to me? And the same is true for customer support solutions. All those chatbots you're building. You'll never know if the customer in the end is really satisfied, or if it's not, without asking him. Just from watching his chat and learning from that, when he stops talking to you, this could either mean he's satisfied or you lost him. Another thing is, if you have lots of data from the internet, like you learn on textual representation, you learn the bias that's in the data. There's one really like shocking example of that. It's with conceptual similarities from word embeddings. You learn the concept or the conceptual representation of what a word means by looking at the surroundings of that word in all documents in your corpus. And what you get is a vector for each word, and you can do mathematics with this vector. You can subtract vectors or add them, and so you can like do this king minus man plus woman vector, and you get the resulting vector for queen, or approximately that vector. That's very easy. But for many corpuses you establish from grabbing the web, your model will also give you doctor minus man plus woman is not a female doctor, it's a nurse. So if you apply that to your chatbot or your website, welcome to your racist, sexist chatbot. This is basically what happened to Microsoft like 2 years ago when they trained a chatbot live on social media. AI systems have some unfortunate breakage of patterns we, as an industry of software developers, tried to come up with to improve the quality of our systems. One thing is you cannot break it down. Like, you have to train it and run the training on a given test set to see the results. There are no units of work inside that machine learning part, or that you can come up unit tests for. So there's no isolation. Also, that leads to a larger dimension of possible failure space, because it's not only the algorithm and the implementation which could be wrong. It could also be your model or your data, and that leads to 1 or 2 orders of magnitude higher failure rate, or failure dimensions. Sorry, I put the link down there. I'm not sure if you can read it. That paper contained a lot of potential failure sources mapped onto those dimensions. Whoever is interested in that, just follow the link. And one more thing, and that's why I chose the AlphaGo example. Machine learning systems have or most of the time, sometimes, a non-stationary nature. If you train a system and retrain it over time, you have to accept that the whole system you see and you have to debug is not only your current system, but also like way back. If AlphaGo had decided to go another way, or decided, you know what I mean, to go another way, like 20 iterations before, I would have another model right now. So you have to know that and have to take that into account. So that's another thing you have to know. It's still software. It's still prone to some hacking. Each AI system to a different approach. This one is really interesting. As a group of MIT students, researchers, they 3D printed that turtle and painted it. And when you hold it into a video camera and feed that video feed into the Google image labeling tool, API, whatever, at that point in time, Google always told you that's a rifle. That's not a turtle, it's a rifle. From every angle. It's really impressive to see. And that's basically the reason behind this. You can fool deep neural networks with noise you put, or not noise, but with something like that looks like noise from the outside on top of the input to trigger certain neurons. So you can also do that in voice recognition and whatever depends on deep learning. So go have fun with your Alexa. So what you need is a new set of quality management tools, or new, improved, whatever. One is, if you depend that much on input data, you have to take quality of your input data into account. That's what a lot of people in AI usually neglect. They're taking input data which is either available or easy accessible, like scraping websites. You automatically run in this bias problem I mentioned before. So managing quality of input data is like have metrics on it, visualize it, try to understand what you're pulling in. Identify bias in that data, identify missing categories. Like there's that other, sorry for hitting Google that hard, but they are upfront and they made a lot of mistakes. There's this famous flaw in the Google image search, which was obviously trained with pictures of white Americans for a large degree of the training data. And they were unable to identify black people and labeled them completely wrong, which is, yeah, the machine learning just reflected what you put into it. I had that medical data example. For things like that, you have to establish panels of judges to say, okay, this is my input data, and I expect this outcome, and if I miss that outcome, I have to flag it. And unlike many other problems in AI, you often have the problem of your changing problem over time. So you have to have these judges for the whole time your system runs accessible. Just having an expert once and let the machine learning do whatever it wants afterwards is just not enough. And the last thing here on input data is if you take in real input data, you don't know, or sometimes you miss patterns in there. And you cannot be sure whether your AI has a high recall, meaning getting out all the labels you expect, if you don't know what's in the input data. One way to cope with that is to inject generated data into your real data set, where you know the properties of this data set. One thing for all the people working in QA here is really get rid of the idea that a test is green or a test is red. You have to work with test sets, and you have to accept that like 90% of your tests are okay and like 10% are failing. And even with that, that's not enough, because you don't know which kind of failures you have. You saw the confusion matrix Laurent put up. That's one mechanism of like looking at what the quality of your machine learning. For non-stationary tests, you need to have something like I accept it getting better in order to get, you have to accept it getting worse at some time in order to get better at a later time, because otherwise you'll be stuck in that local minimum. The picture to have here in mind is what Laurent showed with that curves, where if you don't accept becoming worse, you get stuck in a local maximum and don't reach the optimum. 5 minutes? Okay. And it's not enough to test outcome. Instead, you should look at the inside, to do white box testing. I have one rather intriguing example of that. A colleague of mine took part in that RoboCup simulation league, where you play soccer with little software agents. And he had a team which was really, really great. They made a lot of goals, but never ever they were receiving a goal. And this is great, obviously. But when he looked at it, he realized he made a mistake in the implementation. And all those agents representing the player were behaving normally, but he missed a flag which made the goals or the goal posts immutable or immobilizable. So the goalposts learned to avoid an incoming ball. And if you see just the output, you won't get that. You need to visualize, for example, the movement parts of the agent. And if you see something like this in your patterns, in your output, it immediately gets your eyes. Last but not least, if you need to accept failures, you have to add a safety net. And you can have that safety net also in development. And if you hit the safety net too often with a model, it's obviously not OK. One thing I just want to mention, because it's really hot in research right now, is to break up or to extend machine learning black boxes by adding explainability. There's especially an EU legislation, I'm not sure in what state it is, which demands that autonomous agents making decisions should be able to explain them. And one way to do so is build another layer on top of the machine learning to locally re-inspect what's happening in there. Very, very interesting. Very right out of, or not out of research actually, but in research, definitely worth looking at. Very interesting things. So I'm almost done. I just want to give you two general ideas on your way out. If you forget everything else from my talk, just remember those two things. One is the speed, cost, benefits of machine learning often apply only if you accept failure. So please think twice before implementing something which is high stakes and has no acceptable way to cope with problems. I've seen people applying AI to HR on a global level to screen candidates. That's a bad idea, because in your human HR department, you can diversify your HR department to fight bias. There's no such thing for machine learning. If you don't know how they trained it, don't trust it. And the other, my favorite idea of how to apply machine learning is use it to derive new knowledge and use that knowledge to solve new problems. Thanks very much, and stay curious. If you want to reach out, there's my shortened Xing link, and you can find me on Twitter at Chris_Betz. Any questions? I really can't see any hands on or not. Ah, here's one. Okay.
So I'm one of the QA and test guys, by the way. So the interesting question is, mostly systems fail because we couldn't imagine upfront what could happen or what will happen. Therefore, if we apply this to AI, the same will happen because we never can foresee what might happen. And I see already kind of this as a game that people spray basically random noise on your road, and then your autonomous car get nuts because there's noise on the street because you couldn't foresee what will happen. How do we do this? Because we're talking about a ton of data. We cannot use a human to evaluate if this upfront input signal is this strange noise that leads to a wrong decision. Will this lead to, you always have to have 3 AI systems independently programmed, running next to each other on different hardware stacks, and then we make a, majority win decision?
That's a really tough question. I think you have to switch your mindset a little from what you did in QA to something like you act as a pen tester. And you can't act as a pen tester if you don't know what happens inside. When I compare it to classical programming, as a quality engineer, you rarely need to know which kind of database you're using, because the failures in the database are handled by the database provider, vendor, whatever, and it rarely hits you systematically in your output. Happens, but rarely, and the stakes in AI are really higher. And with that, with the tools being so diverse, every AI algorithm, even every deep net implementation has its own set of problems baked in, as a property of what it is, like the thing I showed with the turtle. The benefit is it often applies to all the problems. So if you see it in computer vision from MIT, like with the turtle, the same problem must be there in other areas using the same technique. So I really believe you remember, or I'm not sure if you remember Laurent's scale, having a lot of developers on this side using the API, and none in your team on the expert side will lead to failure, although the API from Google is really neat. It's great, but not knowing what happens will not enable you to test it. Okay, hopefully this answers your question. Also, I know it's not do this and you'll be happy.
Okay, then let's summarize this quickly. I would basically use AI and machine learning, or basically machine learning, or AI, whatever, for everything that's non-critical. So where you can afford, basically, right now, maybe for the next 10 years, where you can afford failure. Where you can't afford failure because you diagnose sickness or death, or maybe you use this for autonomous cars or tanks. It might not be a good idea to just rely on this completely. Or you do the famous NASA thing where you have 6 different systems running concurrently, and then you will see who wins. But if you use the same developer base, then of course you have the same problems.
Yes. Yes, I actually think so. I think AI is not ready at the moment to be the only system out there, for example, to drive an autonomous car. Because it is prone to some extent to failures. And that's basically, if you look at what happens to all those Tesla having crashes, I read 3 or 4 of those incidents, and it was like, okay, it's really hard to identify a non-moving object. Like the first, which was very popular, was that road sign across the road. It was like, it's not moving, I don't care. That's nothing I trust. It works for like 99.9% of the time, but unlike a hard disk failure, for example, where I switch back to another server and everything is fine, except I have something to repair, I'm dead afterwards. It's not okay, it's not acceptable. And yes, I think driving with cars with no fallback mechanism is not okay. And having that alerting mechanism, for example, to tell the driver he's in charge now, hey, that's bullshit. Like, if it takes me a second at the speed of 150 kilometers an hour, I'm gone like, I don't know, but I think it's something around 300 meters or so. Yeah, if the obstacle is like in 200 meters, a second is not enough. Yeah. You know.
So thank you for the talk. Can you provide an example of deriving knowledge using AI? That I can't understand that because you explained that AI is like difficult to debug and to understand how it behaves and so on. So can you provide an example on this?
I don't have an example at hand from AI. However, I have an example at hand, and zwar it is the from Jon Snow in 1853 or so, who found the cause for the cholera epidemic by mapping the cholera cases in, I think it's London, Broad Street, and finding out it's all close to the location of one well. And that way he was able to say, or to prove his hypothesis that it's something in the water, not something which is spread out in the air, not by inhaling some bad air. And the same thing you can use AI for. You can cluster your data and see correlations in the data, which is so complex a human alone cannot see. So my favorite use case is use data visualization, use artificial intelligence, and have it interact as data science tool, whatever, and use whatever you learned from that in your product.
Okay, thanks.
Okay, no more questions? Thanks a lot. Stay curious.